Hello everybody and welcome back to another video. Today what we're going to be talking about is the iterative design process and how do we actually design things to be iterated on. This is a pretty key principle when it comes to designing robots and just a lot of things in general, because the likelihood that something's made and it works the first try is very low. So we want to be able to design so that if we make a small change here or we change one part, we don't have to change the entire thing. First, let's look at a bad example of this. So some of y'all may remember from the last video where I talked about this combat robot. This is an example of not a great design to be able to easily change one part of. Because, for example, if you change the diameter of the weapon, the entire rest of the robot has to change. There's not okay, I'm just going to make it like 10 millimeters bigger and not have to change anything, because everything is linked to your weapon geometry when it comes to combat robotics. Same thing for my wheels. Say, I want to make my wheels 5 millimeters larger in diameter, or 5 millimeters larger in width or depth. That's a very big change, so the rest of your robot kind of has to change. So this is a bad example of how we design for something to be able to be iterated on for those reasons. There's a few things on here that are not that bad. For example, this top plate, pretty easy. It can be easily changed or modified depending on the dimensions. If you change the chassis, the top plate changes realistically pretty easily compared to the chassis. Whereas if you move the weapon up, it suddenly changes the geometry of the rest of your robot. And that's makes it very difficult to say, okay, I want to change my tooth profile or my diameter and not have to change the rest of the things. It makes it challenging. Let's look at some examples of better designing to be able to have things iterated on. Let's look at the first concept for that. The first concept is isolation. So if we notice here, this is a 2025 FRC robot. We're looking at the end effector. So this is the part that would pick up the coral off of the substation, if I'm remembering correctly. I graduated in 23. So let's take a look at why this is a pretty solid design to be able to be iterated on. First, we notice that the motor is down here. So we have a motor down here that doesn't really affect the behavior. Oh, let's lock this. The behavior of how this rotates or how it's going to be able to perform its task. Comparatively, say we had to move one of our drive motors to be able to run our wheel, suddenly everything else changes. In this case, I could move this motor down and all I have to remake is this plate. I don't have to redesign the whole intake or this whole assembly, this whole carriage assembly. I just have to remake this plate. So that's sort of one element of it, is we want to design for the least amount of things to be impacted when we make a change. The other thing is swapping of subassemblies. So when we design stuff, we choose to make things into different subassemblies. In this instance, on this robot, you can break it down into several different subassemblies. You have climbing, you have intaking, you have outtaking, and you have an elevator. So that's 4 different subassemblies. And then we can break those down even farther into different elements. So for this intaking subassembly, we have these plates that hold up the motor, but I would call that separate from this end effector element, because do you see how the motor is on the end effector? This makes it so that if I wanted to change where this motor was or anything about what's inside of this, I could completely change this to a whole different design, like an entirely different design, and it wouldn't affect the way the rest of the robot works. Something that's a little bit different is the climber down here. If you wanted to change how the climber works, it's going to end up affecting probably the way that you intake and how that happens. and the way that all of these parts have to move, and this plate goes up and down, and the geometry of that, and possibly even the geometry of this hopper system, it's going to change that if you choose to change the climber. So it really is dependent on what you think you're going to be changing a lot of. If you know that you're going to be changing the end effector a lot, high probability of that, anything that you're intaking or outtaking game pieces directly with is probably going to change over the course of the season. You want to be able to make it so that you can easily iterate and change on that element without it necessarily affecting your whole robot. Whereas something like your climber, it's not as pivotal that you're going to be rapidly iterating and making changes between every competition, and just in general to be able to make it a little bit better, a little bit more optimized. Once you have a design, you're pretty much going to stick with that design for the rest of the season when it comes to these larger elements. So you don't have to worry as much about how it might interfere with the rest of the robot. Let's look at a 2023 robot, for example, as well. In this case, we chose to say, okay, we're going to have a horizontal elevator, right? This constrained us slightly into having to have intake geometry, this element right here, that worked with an angled elevator, not horizontal. So we constrained ourselves to that subgroup of elevators. However, we made an educated constraint there by saying we know that no matter how our intake looks, we want it to function in this angled elevator fashion. So we didn't have to worry at all about that for the rest of the season. The only thing we changed was this element right here. How do we modify and change the intake? And all of these plates are really easy to change, right? I could completely remove this, take and put a different one on, pretend it's a different version, and it'll work the exact same. I don't have to change anything else about the rest of this robot because I chose to be able to isolate this subsystem from the way that the elevator works. Okay, how do you actually do that? In this case, the way that we did it is by using these tubes. These tubes have lots of holes in them. They're called max tube. They're made by Rev. And they allow for us to be able to easily interchange components on and off of them because they have what's called a hole pattern. This is the same as a go build a hole pattern or a Tetrix hole pattern. They're all called hole patterns. It's just a pattern of holes that you can use to be able to make mounts to, easily assemble things onto, for this exact reason of I'm going to make what's called a superstructure. That's, for example, if I was focusing specifically on this carriage, these 4 beams right here make up what's called a superstructure or an overall geometry. And then the intake makes up the intake geometry. So I could change these plates. I could put a big hole in them. I could change the location of this hole back here. I could change these holes slightly. I could say, oh, I don't even want a piston on this anymore. I'm going to make this have a motor, and not have to worry about changing anything in regards to how the elevator is made. This is an example of good design for iteration. And this was actually iterated over quite a couple of times, and never once did we have to change this superstructure geometry of the elevator. Here, I'll take you through some examples. As you can see, there's lots of versions. Oh, like if we have a first version of an intake, very crude, we can see that this isn't like at all anything what the end product looks like, but it's a great start. Okay, this is sort of what I want to make. I'm now going to refine my design even farther. So I took that design and was like, okay, let's make a slightly refined version. Let's take a look at version 3, but it's really version 2. Okay, this is much more refined, right? Like I have a lot more about, okay, I have my rollers in here. Here's actually where I want to end up mounting my piston. But you can see this back mounting point never changes. It's always going to be these 9 holes, no matter what design iteration we're on, because we chose to design around that superstructure. You can see even more modification and iteration, even more modification and iteration, changing everything else. Oh, let's try an under. How does that work? And change the rest of our geometry. Seems interesting. You can really selectively choose to iterate different ideas. And as you can see, even through these different assemblies, you can see that we chose to iterate on different aspects and how it doesn't really have to change everything else inside of your mechanism. So if I wanted to change from metal gears to 3D printed gears, they're just put on hex shafts. So I don't have to worry about changing this plate or this plate or this plate or how the rest of it works just because I want to switch to 3D printed gears. Or if I wanted to change to different size top rollers and bottom rollers, I don't have to worry too much about how the rest of the intake is designed to be able to do that. That's the goal of designing for an iterative process. Now let's take more of a look of how can we actually achieve this. This is a drive base. It's not for FTC or FRC, but it still highlights this principle really well. I want to let you guys take a moment to guess why this is easy to prototype off of and also easy to be able to iterate off of. If you said there are 3 tubes right here that have lots of holes on them, there's a plate here that has a lot of holes on them, and each of these side plates, you can't really see this one, but these side plates have lots of holes in them, you'd be correct. And the reason is, say I want to put an intake onto this robot, right? I have a hole right here. I have every single one of these holes on this side, and I have all of these top holes to be able to mount something on. I never have to change the way that this drive base is designed, and I could put an infinite number of different intaking and outtaking elements onto this robot, and it would still be able to easily do that without having to ever change how this drive base is designed. So we actually made this drive base out of metal, so it's never going to change, but when you design it so it's not going to be a limiting factor or constrain you in a specific way, it makes your life a lot easier. Whereas, again, if we circle back to this robot, I hope that you see now even more that the way that this is designed does not lend itself to creating different versions without everything about it changing. Because I can tell you, as I go through and change each of these individual parts inside this part studio, everything else correlates to you having one part. And that's kind of the problem with working with something really small, but it could still be designed in a better way to make it so I want to change my wheels. It's substantially easier to do that than how it is designed right now, where this armored piece interacts with the body, it interacts with the upright, it interacts with the wedge, it even in a little bit interacts with the weapon and how that's designed, because you have to worry about these screw holes and everything. But it makes it really challenging to be able to say, I want to change this little part, so everything's going to be able to have to change. So just to go over that again, designing with change in mind. So designing to have lots of attachment points is really helpful. So for example, if I was using GoBuilda, putting a GoBuilda beam right here where I can attach of lots of different elements onto it wherever I want is very helpful later on in the design process. So you're trying to take subassemblies and make them almost completely isolated from each other, like in the case with this robot right here, where the intaking element was completely isolated from the elevator. The elevator did not really interact at all with any of the features of how the intake functioned. I hope this cleared up some ways to do iterative design and for multiple versions, and also gave you some great ideas of how you would go about designing some sort of robot or just other project to make it easier to iterate on later down the road. Thank you so much for watching today, and I hope that you have a fantastic weekend.